All right, folks, we're going to get started in just a minute. So, those of you who want CME, please sign in on there's a message board back there. I guess we got one slide ahead of ourselves. Text into the system. So the text number's on the back table there if you need it. A couple of announcements about some upcoming talks. So we're excited to have a couple of other speakers coming the next week. So on Friday, particularly for the residents, we have a speaker from University of Texas in Houston, Dr. Barasco. I hope I pronounced that right, but anyway, she is their vice chair for quality and safety, and she's going to be talking about social media and utilizing that to build your academic career. So I think it'll be a really enjoyable talk. That's in the Meyer 1 conference room back in our clinic offices. So please come to that. And then next Wednesday, the 21st, we're going to have Eric Wazotsky, who's Director of Cancer Rehab at NRH, and he's going to be giving a talk at noon also, and that'll be in FIPS 240 on cancer rehab. And it'll be an interactive talk, so we're looking forward to that. So I have the pleasure to introduce to you all somebody who's very familiar to those of us that have been in Hopkins a while, because Dr. Dillingham spent 10 years here back in the 1990s and early 2000s. Now, he hasn't been back in 15 years, so we're happy to have him finally back and talking to us. He's chair of the Department of Physical Medicine and Rehab at UPenn, which is the oldest rehab department in the country. He's a world-leading expert on amputee care, and he's going to be talking to us about a neat new adventure that he's been on, developing a new type of prosthesis that will hopefully reduce cost and make it much more efficient to provide amputee care. So with that, Tim.
Well, thank you. I'm really delighted to be here. I remember talking with Marlise, and Dr. Gonzalez worked with me many years ago on one of my research projects, and she got Dr. Mayer to invite me to this talk, and I'm just delighted to be here. It's nice seeing some of my old mentors. I don't know, the residents, familiarity sometimes makes you not realize that you have a giant in our field in your midst. Dr. Barbara De La Tour has just been tremendous. She was a mentor for me. And having her around, you should cherish every moment that you get to work with her. Pablo, I remember when we hired him as a resident, I thought to myself, I looked over his CV and I thought, wow, I couldn't get in this residency program. And I said, he's going to be a superstar, and now he's your chairman. Sam is your residency program director now, and he was a former Elkins Award winner, and so he knows the way for you. And listen to your mentors. I'm really pleased that you came here, and I'm going to talk to you about, and I usually walk around. I went to a course on how to teach, and they said, you never stand behind the podium, but I'm told I have to be in the focus line here for the camera. So I'll try to make do with that. I'm going to talk to you today about a project that's been going on for about 8 years for me, and it's developing an immediate fit prosthesis. The goals will be of this lecture will be to learn some of the global needs and the U.S. needs, learn how this sort of came about, its key features, and I'm also going to present some preliminary research on this device. Can't do that. No. Nowadays, it's really team science. Nobody can really do anything by themselves. You have to have collaborators, and I have a really terrific engineering team in Milwaukee, Pewaukee, Wisconsin. Dr. Jim Marshallak and Connor Duco and Sarah. We do most of our patient research and patient testing at University of Pennsylvania, And then I have business development, Josh Mullins, marketing, Michelle Brass. And so you have to kind of bring this whole team together to make this work. Now, this is the first lecture I've ever given where I have disclaimers. This was funded by the National Institutes of Health for a phase 1, 2, and 2B, and then a commercialization project is what we're funded for now. I'm the PI, but I also founded the company, and I'm the major owner of the company as well. All conflict of interest was signed with the University of Pennsylvania as a primary investigator by the provost. All of the amputees you see in here signed consent forms. We're very HIPAA conscious, and there are several patents associated with this work. So, why do this? Why do we need a new state-of-the-art in prosthetics? Well, there's a huge and unmet need out there. This is according to the, actually Dr. McKenzie here, about 1.6 million amputees are living in the U.S. With an amputation, with a limb loss. And because of the survival rates, this is going to double in the next several decades. About 160,000 new amputations occur each year in the United States. And as we all know, these are the major causes of limb loss: dysvascular, traumatic, malignancy, and congenital. And we did a study here a long time ago that actually hasn't been duplicated. It's hard to get funding to just do epidemiological studies, but we showed back in 1996 that dysvascular outweighed traumatic by about 8-fold. Cancer was way down, and congenital deficiencies were pretty constant. Over a period of time, what we found was that the dysvascular rates were going up, and this was from 88 to 96. Trauma had gone down, and this was probably due to better workplace safety, less manufacturing, industrial labor in the United States, and cancer was going down as well. That was a very, 1/100th the overall magnitude. Now, I did find some articles recently looking particularly at diabetes. Now, the figures I just quoted you were for the general population, but for diabetes, there was a big push to reduce amputations, and by better health system performance, guidelines, clinical care issues like inspecting your feet. And what some of these researchers found was that indeed the rates were going down. So you see the rates in diabetes, and my rate, the overall population is about 46, so 10-fold difference. Diabetics have a 10-fold increased greater risk of limb loss. It dropped pretty precipitously over this period of time. One of the important things to note, though, is if you have end-stage renal disease, you have about 100 times greater likelihood of losing your limb than if you don't have diabetes or renal disease. And some other, but in the Scottish registry showed decrease as well. And this New England Journal article was quite strong. They used a lot of data sources and found that there was a 50% reduction in amputations, and they thought it was mostly due to advances in healthcare, medical homes, and overall better health system performance, not any change in the diseases. And this is my crew up skiing. So worldwide, it's a fairly bleak story. 80% of the world's population live in developing countries, and it's estimated that about 25 million need some prosthetic or orthotic, and 75% of developing countries lack any prosthetic or orthotic training programs. So they don't have the educational infrastructure to meet the needs of their countries. This is from the World Health Organization. Traumatic injuries. This is a study out of Pakistan, and the problem with developing countries is not so much that the accidents are worse than here, it's that you don't have the trauma care system that can then pick up the pieces, and what would otherwise end up in an external fixate or a vascular repair and a stint on rehab ends up in an amputation. Landmines are another source of limb loss in other countries, and the takeaway with this is that less than 1 in 4 landmine victims are fitted with a proper prosthesis. And this was from some of the World Health and Foreign Policy Agency. This vascular disease, much like in the United States, it's also going up and in developing countries. And I know this is hard to see, but you can see there's sort of a diabetes belt here where the prevalence is going up in these areas and correspondingly leading to more amputations. Diabetic foot care is also lacking, so that when you get an ulcer, it more often leads to an amputation as opposed to being able to be healed. Barefoot walking, lack of awareness of pathogens, and just by the time somebody gets to a medical facility, it's already infected and you have osteomyelitis and subsequent amputation. This is an insightful study, and it was from the International Diabetes Federation, showing that in developing countries, the rates of diabetes are going up for the middle-aged folks as opposed to developed countries where the diabetes is going up more in the elderly. Oh, and by the way, feel free to just shout out a question if you want. I don't want you to have to wait till the end of the lecture. You have to have training programs for prosthetists and orthotists. And so for developing countries, access, labs, materials, and time. And making a prosthesis is time-consuming. It takes weeks to fabricate it with molding, as we'll see in a moment. And as you all know, that first year after amputation, you need several different socket changes because the limb matures and changes. Can everyone hear me, by the way? Good. And it's a particularly problem if you don't have a prosthesis, because many countries are not wheelchair accessible. You'll be wearing crutches. And so you really need that prosthetic to help you get around. Now, how many people have watched a prosthesis get made? Yeah. So it's time-consuming and often technician intense. It relies on craftsmanship, so it varies. It varies based on the prosthetist as much as the person. You have to make a positive mold, build a socket over it, do a check socket, sometimes a final hard socket, and you have to do different adjustments to make it work. This is what you typically see in a lab. So you have to take a positive mold cast of someone's limb or digitize it and then create a positive mold. And you have grinders and you have mandrels, and you grind the plaster where you may think the patient has a pressure-sensitive area. And if you go into these labs, a lot of times you smell dust, dried plaster. It sort of gets my sinuses all plugged up. But this is kind of the state of the art at this point. Now, there's some new things. This is my family. We had a meeting in Hawaii, and if you ever get a chance, go to Hawaii to a meeting. It was really fun. I was the keynote speaker at the AANEM that year, and my kids still talk about how much fun it was. So the fundamental problem, I think, not only the manufacturing of the prostheses and how time-consuming it is, but and even when I was running the amputee clinic here many years ago, the fundamental problem is trying to make a hard, rigid socket fit a soft limb with bony prominences. So whatever you digitize and make and create in that hard socket, the minute you walk on it, it's different. Many things are done. You can grind out the inside. You can make cutouts. And I imagine most of you have seen this done in the prosthetic clinic. Socks, increase and decrease socks. So it's really time, I think, for a fundamental change in how we approach these patients. Now, there are some other things going on. 3D printing gets a lot of press. It's not bad. You can digitize images, have it printed, and as you'll see, what we used to, with our engineering folks, would make 3D parts when we'd want to make a design change. They'd make a 3D part, but they had to laminate it with epoxies and make sure that it was strong enough. And so you can make 3D printing pretty strong if you do the right things. but again, it leads to a hard socket.
What about the 3D printing for upper extremity? Is that the same problem?
But it is. It is, but with the upper limb, you don't have to weight bear.
Right.
So you don't need it as strong as you would have for the lower limb. It's not as much of a problem. And frankly, 3D printing has a great role, I think, growing kids. I think, you know, being able to 3D print and mail something to another country. You know, I'm just sort of going through, I'm not trying to disparage any of this other technology. I'm just sort of imparting knowledge and showing you what else is out there. So a lot of people have used PVC for these third world country prosthetics, and again, relies on a lot of craftsmanship and sort of one-off manufacturing. A lot of these materials aren't durable. As you'll see, you have to have a bloody strong set of materials to withstand a 300-pound guy walking around. And that's why you have international standards for testing. They often have a high probability of breakage. The other thing is, this is really, you can get a socket that fits pretty well, but you got to get the alignment right, or it's very uncomfortable and can be just not working well. The other thing is you have to think about suspension systems. And there are a lot of them out there. Pin, sleeve, magnet, suction, automated suction, you know, the little machine. But you have to think about it, how it fits in the overall system. This was the pediatric folks, and probably a very good thing to do. Orthotics, I think, are not bad for this because people grow quite a bit, and the ability to rapidly give a patient what they need at that time, I think, is really, really critical. We actually know that our rapid prototypes would work when I tested them in the lab because our engineers would make the 3D print. We would make several of them, and they would break one. And so they could tell us, and we would ask the engineers, if we're trying a new design, as we'll see in a moment, we would ask the engineers, we want the socket a little bit bigger for this particular set of people, and will it withstand the rigors? Can I let that part out of the lab? And that's a key concept that you have to keep in mind as I present this talk, is this is not like general research, because we're developing the product in parallel with having to test it and determine it. So there's these key milestones, like, is that part ready to go home? Do I feel comfortable letting somebody take it out of the lab? And you have to have a lot of engineering behind that to determine that. Whole bunch of international efforts have looked at low-cost prostheses, and OSER has a modular cast system that's fairly common in Europe, where you actually cast right on the limb. Problem is, it's very hard to get pressure there. They have this vacuum device that puts pressure and makes the cast squeeze it, and again, you end up with a hard socket. This was an effort. This reporter was from the New York Times, went and looked at one of these fitting centers in India. And, you know, I don't want to disparage, and please don't think I'm doing that, disparaging efforts to help people. It's all good. Just pointing out some of the shortcomings is that many of these folks, once they got the limb, it was so uncomfortable that they went back to crutches or discarded, because if you don't get the alignment right, and that's very hard to do with prostheses like this that have no adjustability between the socket and the foot. In Haiti, for instance, very well-meaning efforts donated a lot of componentry, which then had to be retooled and refabricated to make prosthetic components. This was a quote that said, most practitioners in the United States, this was from humanitarian reliefs, see 700 amputees patients in a lifetime, and they serve that many in just 9 months. So it really illustrates where you have an earthquake and a lot of crush injuries, and crush injuries can't be saved. You have a lot of limb amputations. So how do you address this? Well, you have to, in some way, you have a high need internationally, you have a cost pressure, you have a pressure to get devices to the right place, you have a need to make them quickly. And so mass production really offers a great alternative to some of these problems, and particularly injection molding, as we'll see. With those types of manufacturing, you can automate and optimize the design and control the quality. You can build in adjustability. You can have very high strength materials. As we'll see, the materials we're using are called aluminum substitutes. So they're plastic injection molded, but they're as strong as aluminum. Not as strong as steel, but they're as strong as aluminum. And they have great properties, but the properties are a little bit different. So they're not exactly like metals. You have to look at how many stresses and repetitive stresses they will take. We also incorporated commercial feet and componentry, and it was very interesting initially. I started this at the medical college trying to get a very low-cost prosthesis. And I initially set with my resident a cap of $300. And the problem with that is it constrained your thinking too much. If you try and set these a priori cost pressures, if you're designing a product or something like this, it keeps you from thinking outside the box and doing things that would get a better product. So I came up and we just sort of lucked into the paradigm that get the right design and then drive down the cost through economies of scale, manufacturing, and things like that. Even here, prosthetics are very expensive. And there's a patchwork of insurance. I'm sure you deal with that quite frequently about who will fund prosthetics. So where do we go from here? So I started iFit Prosthetics about 7 years ago, mostly as a vehicle to apply for an STTR grant. And it's been quite an adventure. So many failures, but as I'll convey in a moment, those failures are the most important thing you get. And you have to have those failures be quick, cheap, and fixable. We initially tried rapid casting. We tried different materials. We finally coalesced, and I spared you all the mishaps that we had for this talk because it was only an hour. And we have till what, 1 o'clock or 1:15? What's the? 1:30. Great. We finally coalesced around the device that you'll see. It's very important when you're doing this. It's not like traditional research. You have a paradigm, you collect data, you analyze it, you write it up. Here you're collecting data, but you're also designing and changing the product. And so you want things to fail quickly. And the kiss of death for this is when you cannot wait for the next semester and a new grad student to come and help you. You need it done in weeks rather than in months or a semester. I strongly urge you, if you ever do this, to get a for-profit company working with you. Advanced Design Engineering that we work with in Pewaukee is absolutely terrific, as Josh can attest. We have twice a week go-to meetings where everybody sees each other. It's video conferencing, and we problem solve. And if there's something wrong, like we recently had a buckle break, so we had to retool that, we retested it, we reprototyped it, and we did that literally in about 2 weeks. You can't wait a year for this, or things will just never progress. Then there's the issue of when are you ready to finish the product? That's always a very challenging thing to know. When is it good enough? When is it good enough that you can take this and give it to someone and be confident it's not going to break, they're going to fall, and they're going to end up in the hospital with a hip fracture? I mean, this is real stuff. And it's what keeps us awake. And so what you have to do is you have to have an engineering arm that can test and give you quantitative information. Does it work? Is it strong enough? Will it work? For the first, 3 years, we've been just at the lab at Penn, and then it was in my lab in Milwaukee, working with patients and making sure in parallel bars and in the lab that they were safe. Then what you have to do, so you have a lot of design iterations. Then the way we're making this product is with injection molding. It's state-of-the-art injection molding. You melt these glass-filled nylons under 1,200 degrees. You inject them under high pressure, and you can make things mass-produce, very consistent parts. The problem is is for every part on the prosthesis, you have to make an injection mold, and they're very expensive. So when are you at the point where you can say, yes, we have the design, and I can now spend $25,000 of the grant money to have these molds made? So that's that big step where you hum and haw and you get more data and you try to test patients. And at every step of this, you can't test 100 patients or collect data on 100 patients. It's really a handful. So those handful of patients that you're seeing in your lab that you can recruit from advertisements are the ones that are actually driving your design decisions. So it's a bit freewheeling. I was going to talk a little bit. I didn't want to talk too much about it, but if anybody's interested, I'm happy to answer questions after this lecture on STTR grants. They are like SBIR grants, but they have some nuances. The primary investigator can be employed by the academic institution as opposed to the business concern. It's designed for testing and developing devices like this, and the university gets about 30% of the effort. The company uses the remainder. And there's a series of phases. Phase one is this proof of concept, and it's usually a one-year grant, and where you can write and get funding to see if it works, test it out. Phase two is, and to apply for phase two, you had to have gotten to phase one. So the group that's applying for this is pretty rarefied, and you have a much better chance of getting it if you've done a phase one and you get a proof of concept. This is about, I think it's up to 200,000 now. This is up to 2 or 3 years at about $500,000. So it's a considerable chunk of money that you can use to do it. You think you're going to get it ready, but you're not. By the time you get to the end of this, you think, geez, this is not going anywhere. And so they have a phase 2B or a phase 3. You got to watch the agency because the NCMRR didn't have any phase 2B, so I had to go to the National Institute on Aging, and they subsequently funded it. My research assistant found a commercialization grant that was a pilot grant by the National Institute on Aging. We slipped in 2 years ago and got funded by it, and now it's no longer in existence, which is really, really lucky. And what people refer to when you read about this is this valley of death. You can have a product or your final design where you think, yeah, this works pretty well, but then it never goes anywhere because the prosthetists don't like it. And I could go for an hour talking about how I had made this really neat design that I thought was just great. The prosthetists hated it, so we had to change it. But this is really the problem in getting a product from the bench to people. So the STTR, you have to have a small business, for-profit company. It has to be wholly or the majority American-owned. They ask you a whole bunch of questions, are you doing business here, you doing business there? All manufacturing has to be done in the U.S. If you're funded by this grant. And the grant, really, the goal is to go from bedside to not bench and back again, but bedside, bench, out the door to meet somebody's needs. They want to build American small businesses, and it's interesting because as we're getting more and more producing this, people want to send everything to China. I said, no, you can't do it. We're making America great here. So it's very different. And I tell you, it was a good project for my time in my career because I'd already made tenure and had advanced. But if you're going down this pathway for STTR or product development, it's not traditional. You don't get publications, the traditional coin of the realm for promotions. It takes a long time. You need rapid turnaround. And again, don't rely on the academic timetable. If you have an idea, partner with a business who's motivated to do it with you. Again, you want quick failures. You make designs with limited data, and it's very challenging. And we're at a point right now where I'm now confident when someone comes in our lab for either the study or their meeting with Josh, I don't have this sort of angst that, oh my gosh, are we going to be able to fit them? We're getting pretty confident. We can fit them and fit them pretty comfortably. And so now is kind of the time when, as part of this grant, we have to do a comparative effectiveness trial, and that's where we're at right now. As a researcher, you know, it's hard to wear different hats. You have to be dispassionate and an academician. As an inventor, you have to kind of be a bit freewheeling, and you have to be a salesman when and you have to tout the product or the concept before the science is caught up with it. So, it's, you know, it's a very interesting academic paradigm. In fact, the bioengineer chair at Penn and I are pushing to try and get an inventor track for young engineers or young faculty, so that you can have a set of requirements to get promoted that embraces this sort of concept of innovation. So how do you even begin to decide how to fit a new product to residual limbs? Well, you need some data. And in Milwaukee and in Pennsylvania, we went to labs and we got their old casts, the positive molds, and used that to take measurements and figure out how big a socket you need to make. Well, a couple of years later, we bought a digitized image database from Willowwood Prosthetic Company. And this has been just wonderful, because these digitized images give us quantitative data that we can make design decisions. So our mission is to produce the highest quality, affordable prosthetic device with a key on affordable. One-stop fitting for non-stop living. That was what our marketing people came up with. The right fit right now was another one. You got to have it. And any of you know, when you have a grant or a center grant, you got to put a catchy name by it. You know, the LEAP study or some fit study. So you have to do that same thing here. It's based in Milwaukee, and the engineering team, as I said. The idea is really to grow businesses and to bring small businesses into the forefront. Now, I just show this because there are other people in this space that are working there. This is Limb Innovations. They have an adjustable brim here, and they still have to use 3D imaging, and it's pretty high cost for what you get. The other fundamental problem, I think, that other people in the market are forgetting is, when you make a socket, what do you want that socket to do? Any of the residents?
Fit correctly?
Fit correctly, but in that is total contact. There's sort of two ways that there's schools of thought that, you know, you put a patellar tendon bar and you put much of your weight on your patellar tendon on the medial tibial flare. And then there's a lot of very good studies showing that total contact will get you just as good as suspension and prevent skin breakdowns and problems with that patellar tendon bar. There's some other people trying to really minimalist approach to this. Again, you know, is this going to stand up to ISO testing standards? This is actually an interesting device. It's a Revo limb where they parts of the socket and then have a BOA system to adjust it. And in fact, one of my patients, I've actually ordered this on him because he's an above knee, and we don't have an above knee product, obviously, but it works pretty well. You still have the hard socket here that limits you in opening up and accommodating edema changes. So here's what we developed. It's designed to be in a box, and there's boxes here that you can come see later. It's a prosthesis in a box. I had an idea of, you know, be able to mass airlift this to a impoverished area, and somebody who's not a prosthetist, maybe a fitter who's been trained in how to fit this, can, you know, fit a whole bunch of people and get them taken care of. It's made of high-strength polymer materials. It's mass-produced. Now that we have the molds for this, you can make 50, 500, 5,000 very cheaply. Once the molds are made, the individual parts are $3 to $5, so it's much easier to make those. Here's the device, and we'll see some of this here. It's buckles. I borrowed heavily from the recreational industry, these concepts. It has a blocking buckle system and cables. There's different cables different sizes and a lock here. It has a padded inner liner, and we put the pin lock, it's a pin suspension system right here. We recessed it. One of the problems with other amputees that they told us was a lot of times if you have a pin suspension system, it sticks out kind of like Frankenstein, and they bump it on furniture and it'll come undone. So that's how it's kind of packaged up. We have everything in there except the foot and the silicone liner. So you have the pylon and the cables and the device. Here's the kit that it comes with. And it weighs about 2.9 pounds. We weigh everybody's prosthesis that comes in as part of our study. I didn't present the data, but ours is pretty comparable. But I'll tell you, the range in private, conventionally made prosthetics is huge. We had our biggest one, we just had a guy come in, an 8-pound prosthesis. I mean, it's almost like a bowling ball. You can throw that thing out and it'll pull you forward. So ours fits weight-wise pretty well within the range. And it's interesting because the engineers, every time I want it strengthened up, they say, well, we're going to add, a 1/10 of an ounce. I said, go ahead. Be bold. It's fine. I would rather have it be very, very strong than break. Works with a lot of commercially available feet. We use a silicone liner. Now, we had a mishap in the lab one time where we used to use what was that lock? Not the shuttle lock, but we used an older type of lock. There was a ratchet, and we had a patient in the lab that didn't get down into it, and you couldn't hear when it went click, click, click. So they didn't get down into it and ended up having a fall in the lab. Fortunately, it was very well controlled, but after your blood pressure comes down and you realize that's a problem, we actually redesigned the whole prosthesis so that we could use a shuttle lock, the Bulldog lock, which is pretty standard in the industry. We actually pulled a paper and found out that someone had actually written about that's a probably safer, mechanically simpler, less prone to failure lock. You don't need a full prosthetic lab. That's kind of what you need. You need a torque wrench and be sure to torque these things. You have to make sure that you have to do everything the prosthetist would. You have to put locking solution on it and torque these down to what the manufacturers say. And here's a. Let's see if I can get the mouse working here. There we go. Excellent. Excellent. After he used this for an hour, he was so swollen that his limb decreased. So there's marked volume fluctuations. Your patients with renal disease, heart disease, maybe hypertension problems, we all know how many socks they have to change throughout the day, the different playa socks. And so the ability to just kind of re-squeeze this is very helpful. This is a woman who is in our study, and she had sepsis and lost some fingers and her below-knee bilaterally. And we were able to fit her. This was actually pretty remarkable. And the one thing that you have to watch their hand function, and people have to have enough dexterity in hand function to use the locks and to close the buckles. And when she came in, I thought there's no way she's going to be able to do it, but she ended up being able to. One of our studies early on, when I was here at Hopkins, was that we looked at a large database, and people that had to wait more than 60 days to get a prosthesis had less satisfaction, long-term use and satisfaction. There's sort of this golden hour, and for trauma, there's sort of this golden period for fitting prosthetics when people tend to adapt to them better. We're starting to do some international stuff. There's a woman who works with one of my colleagues in Jamaica, and she's a physical therapist with the Catholic ministries down there, and Michelle's lab's right next to mine, so I talked to Beth Wolf, the therapist, and I said, you want to take one of these down there and just try it out, and give us some feedback, and she went and we showed her how to fit it. I lost my mouse. There we go. That's probably not. After she fit him, she sent us the full story on him. He had been injured in a traumatic accident and hadn't walked in 8 years. He was on crutches. He was saving his money to buy a prosthesis because it's about $2,000 in Jamaica. And he was just delighted with this. In fact, we're conversing with him. We're going to send him different iterations and let him try it out. But I think this illustrates how a therapist can, learn how to put this on and get people in other countries. And we're constantly looking at how to drive down the price of this with a componentry. Maybe we take that shuttle lock out because that's a $100 piece, and we put a little lower cost for some of these efforts. Advanced Design Concept, this is the engineering firm I've been speaking about, and they're terrific. They can do machining. They can do limited production, which is really nice if you're working with an engineering group that can not only do the rapid prototyping, the changing, but the limited production. So they've got the molds, they made the molds, and then they can spit out the products. Now, what's good enough? When is a prosthetic component good enough that it can be sold? Turns out there's this international standards testing. Has anybody heard of that or know about it? It's to test componentry and componentry manufacturers. It's typically not to test sockets, but we put our socket and our connectors on this. It has to withstand about 3 million cycles, and they have some static failure levels, and the static levels depend on the weight limits you want to impose on it. So typically it's about 900 pounds, and this is mucho expensive if you send it someplace. If you try and buy a commercial machine, it's about $250,000. I mean, just eat up your whole grant budget. So what we did is we made our own. And the thing about Advanced Design Concepts and Jim Marshallak is this is an engineering team with a huge bandwidth. I mean, they can do everything from software to prototyping to, if we got a machine, they can build it. And so we have a load cell and a cyclic loader here. And a lot of times the pylon and the parts bend before the plastic here. And you wouldn't think so, but this plastic is advanced glass-filled nylon. It's an aluminum substitute. It's very, very strong. And so we even put offsets on it and tested it under an offset load. Because if you have an offset load, any load here is going to put a higher torque on there and load it even more. But if you're lining it right, every prosthetic is going to have to put an offset to get it right. And so you want your device to withstand those loads. So there's the device. I find this just really neat. And we ended up making a steel plate, and we've tested, as I'm going to show you, this is aluminum. They bend. So we now have a steel pipe that the engineers made so we can put the maximum load here. And we found that our standard size prosthesis went up to 1,584 pounds, and the plastic did fine. We made these new extra wide cups with the idea, Josh has been out working with prosthetic groups, and he said, look, your prosthesis only fit a certain amount of people. We have bigger people that need to be fit. So, responding to the market, we designed an extra wide cup, and we've got examples here. But before you want to put it on somebody who weighs 300 pounds, you better be damn sure it's going to be strong enough. And we're actually doing, as we speak, well, actually it'll be in about a month because we have to send the load cells to be calibrated at another company. But we broke this at maximum, and it went over 2,000 pounds when it had that offset. When it was just a straight up force, it went to 2,600 pounds. Now, the ISO standards say you need about 900. So we think, wow, this is a great factor of safety for engineering. You're in a plane or something, you want your ribs and your mechanics to have a factor of safety. The problem with this is that plastics do some funny things. They creep, they have different changes over time. So we wanted to make sure it was very, very strong. We even tested it, we put it in the freezer and tested it at cold, and then we tested it at hot, about 110 degrees. And the properties changed a little bit, but not very much. we had some problems with our buckle. And you would think a buckle. We initially tried to take ski boot buckles, and I ordered them. They hurt your hands. And even after I'm using it through the day, the ski boot buckles just didn't work. So we had to design our own that were longer, that had a better lever arm, that wouldn't hurt your hand. But we had to figure out how to make them, strong enough. And so
So it's actually 25 pounds in the thing. Real straightforward. And what is this, so pressure? Yeah, that's the pressure in the cylinder.
So, how many cycles do you need a buckle to not break? And you know, and this, it may seem sort of kind of funny. I'm testing buckles, but that buckle breaks, somebody falls. That's the bottom line. Is when you're held together by buckles and cables, and you're walking around, you want that buckle locked, and you want to make damn sure it doesn't break. This withstood 173 pounds, and we figured somebody really strong is going to put about 50 pounds of torque. If you put any more than that, it's going to torque the prosthesis on your limb. This is another gentleman that, it's hard to find the mouse, there we go, that I fit just about a month ago. He has a knee flexion contracture.
I'm standing up pretty straight.
So here was that we decided to go with this componentry. Now everybody asks, well, can it be used with suction suspension? No, it can't. It's like a ski boot. It has overlapping. It's not vacuum tolerant. So we use a shuttle lock. It's pretty standard in the industry. It's very tough. It's not waterproof, we found out. So if we want a water prosthesis, you got to do something different here. But incidentally, all of our components are waterproof. I mean, you can throw them in the ocean and go goofing around. We've now tried a few people. We've given it to them and let them try it out, and they find it's pretty nice. Now, this person, we decided to try a few different things, and I'd like to get the suspension system. Where's the? There we go. The shuttle lock suspension system, although very good, is expensive. So we're trying to. And so we're trying a little different types of suspension. This is the suspension sleeve. These are a little cumbersome, but I think we can probably make it work. The advantage to that is we could make a very low-cost device to mass produce and send to third world countries. We've experimented with a lanyard, and we have this little. This is a prototype. We haven't got a real part for this. We're still kind of mucking around with how to make that work. And most people, the two people that we've sent out with lanyards, they don't like it because they have to sit down. They have to thread that thread through there, pull it, crank it on. People really are liking the pin. So you just go click, click, click. They can hear it. They get that feedback and know they're safely in it. You have to get it safely on. Because you don't want to buckle the buckles and not have that pin engaged or going out the back, and then they're really not in the prosthesis. Now, we have padding, and we use neoprene padding, and it makes a very comfortable socket. It's not a hard socket. We've been able to fit limbs with all kinds of shapes like that, mostly due to this soft inner liner that can, although the prosthesis socket is one shape, it can accommodate these minor differences and geometric differences across limbs. This is probably the best advancement we've had in years. And there's a ski boot company called SureFit that makes a custom ski boot liner. Does anybody know about that? Yeah, they're really comfortable. And we called the company and said, hey, can you help us with this? And it turns out there's a lot of thermal molded foams that change at different temperatures that can mold exactly to the limb. And so we're using an oven, and you have to heat it for about 4 to 8 minutes. It's not hot, it's just warm to the touch. You put it in the socket, and it molds exactly to the geometry of the residual limb. we're just on a call with them, and we are trying to push this to where you don't have to have the heater. It can be pressure and sort of body temperature over time. This was one of our, you know where the mouse is at? Can you hand me the, I can't, it's not, the mouse is, oh, there we go. All right.
As a safety check. Now try the pin is right there in the front. You like that better?
I ain't got worried about hitting my back on the side or anything.
Okay.
Put it back on and scratch yourself on.
Now the pin, you can hear it go click, click, click. Maybe a little too tight. Now make sure that, always go like this, make sure they're tight. Now push the prosthesis off to make sure it's always stuck on. Good. Okay. Stand up.
So you heard several things that are clicking. I'll tell you that audio, a lot of people don't have vision. They have diabetic retinopathy. They can't see that the other little shuttle lock, or the pin lock. It had to turn and you had to see it, and they couldn't see it. So having that auditory feedback is really, really helpful. Yeah, that's what I'm thinking. So sort of continuing here, the prosthetic technology is certainly advancing, but there's a catch. For most people, these state-of-the-art devices are neither obtainable nor well-suited to day-to-day life. And so at the high end of the spectrum for technology, it's not always practical. So we went kind of through this. We have an adjustable socket. The liner is a neoprene. Suspension is pin. Alignment mechanism is your standard pyramid connector. And there we go. We have sizing charts that have been developed. There's a standard, a wide, an extra wide, and a tall. So we can fit most of the people of varying dimensions and heights using these four different sockets. This is a standard. Here's the wide. It has some extra spacers here. And incidentally, every single one of these parts has to have an injection mold. So that flap, and it took just months and months and months to get this flap right. You know, what's the geometry? Because once you make a mold, it's sunk costs. The wide prosthesis, again, you have that. We designed the flap so it could be cut down and you could adjust it if people shrunk. We now have the extra wide to accommodate people just like this. And you see this a lot of times in different centers. They'll have a residual limb wrapping that chokes the limb off, or they dangle their foot over the edge of the bed and they get a bulbous limb. It would be great to show this, but let's give it a try. This is someone fit. We could fit him in like 2 hours. This is the Boston VA.
The Boston VA. This is the furthest this patient has walked within 2 years, based on what the physicians are here, the head of PTs here, the lead clinicians here, and he's in rough shape, he's shown, but we were able to get him up and going. He's able to get into rehab immediately. The next day, they were able to set something up for him. Just because there's a lot of volume changes, that's why it's so long. Traditional sockets won't fit.
So then we have a tall device. We use these casts. This repository of 6,000 digitized images ended up being just a gold mine. So we analyzed these digitized images and looked at what the range. This black bar is 80% of the population. This would be 50%. So we had some realistic, quantitative ways to build into the sockets what would fit and what wouldn't fit. Same thing for males. This was a circumference, and so we knew what ranges, what design parameters you had to put into the prosthesis. This is much better than when we first started this with the casts from prosthetics labs. I'm not sure we need to see, well, this guy walked in, we don't need to see, we have time.
The end of that video. That's just the gentleman who's been walking with a cane for
Part of the thing is we have he came in with a crutch. He's been walking for over a year with a crutch.
Now, at the end of this video, we cut it, but you'll see emotionally, this guy has had tremendous success with the device. I think that this is a real good video. Watch him throw his hands up there.
He got very emotional.
He got emotional.
Now, this is how we looked at a distribution of measurements, circumferences, and we know that our three here will cover most of the waterfront, both for males and females. So here's the beautiful city of Philadelphia. Fitting it, who needs this? Well, it's kind of like fitting any prosthesis. You know, you got to have someone with well-healed surgical limb, no evidence of skin infections. They have to have some we like people to have some touch sensation or intact sensory ability. Ours, you need some hand dexterity. You really need people who can kind of use that. But most people have been able to use it. You need someone with good judgment. I mean, we all have seen patients that. And there's some in our study that, you know, you really have to slow them down and say, you don't fit people with poor judgment. Now, poor hand function and eye function, we've now fit some people who have some real vision problems. You have to work with them a lot. We've kind of worked it so that they can use this and count up the number of slots on the hook so that they hook it at the right place for when they get up. Sure.
So on that, eye or dexterity issue, if they have an assistant or a helper, it actually makes that helper's job a lot easier to adjust the buckle versus having to try to figure out where Mr. Smith is in relation to his sock compliance or where he's at with his sock. So it makes it a little easier.
So, don't fit some with skin abrasions and that. Our standard, why we now can go up to 330 pounds, because believe me, the industry demanded that. Here's what your answer to your question. We have spacers that go in here, and the sweet spot for this socket is the patella sits about right there. And why did we design that? Well, a lot of prostheses, and you'll look at them in clinic, they come up to about here. They really don't go supracondylar. You can have supracondylar suspension. You can have a medial brim type of things in the old days. But we put the patella right here. Now, patella can be down here. I'd rather have it be down here than up here. But it has to be down in this little V notch. And so you have grip above the femoral condyles. And so it gives a lot of stability here. And you use these spacers so that you put a spacer in to get someone who has a shorter limb to be in that particular area. We can fit people down to about 13, 14 centimeters pretty well. So you cut the pylon. Now this is one of your questions here. Look at that. You know what that is? Anybody? It's an offset plate. This guy's a huge knee flexion contracture.
About 40 degrees.
And so that you can get him up walking, and he got up walking quite well. And now you know why we did that testing for offset plates, because that really force multiplies your torque here, and so you have to have a very, very strong device there. What else? Buckling. We tell people to buckle with their hand open like that. You know, the experience you get leads to the design changes. We had one person cut their finger, got a finger cut on the metal part. So he had to go back to the engineering, go back to the people that manufactured that little steel plate, and say we have to coin all of the edges so that they're not just the ones that are sticking up. So, you know, you learn this. Fortunately, he healed very well, and he liked the prosthesis, but every time that happens, you've got to have that cycle of going back to your lab and saying, geez, we need to fix this now. The buckles go here. Now, we have 6 different cables. So the cables, you can change the cables, and you can change where it fits inside the slot. And what I usually do is I'll mark this slot for people after we fit them and say, you know, that's probably the sweet spot here. You can go one or, you know, maybe one notch either way. We have a wearing schedule. I'll tell you, the people that have broke down their skin are the ones that said Jesus was so comfortable that they went out and walked way, way beyond what they should have. I mean, if I have a new boots and I go hike 5 miles, I'm going to get a blister. So we really try and make sure that they get used to this, have a wearing schedule. How well they accommodate that, I don't know. Here's another sizing chart, just shows how the spacers, socket, and cables, we've tried to put this together. It seems to work pretty well for the majority of people we use. Again, component sizing. We now have this extra wide version that goes even higher to about 50, so we can fit people who are pretty big. Yeah. Oh, go ahead. The foam, it's not, but you remember the foam you've got, well, you actually you can't. You can take it out and wash it. So the neoprene, you can take it out and wash it. The people have the silicone sleeve that goes up their leg with a pin on the bottom. Every day they have to wash it with some soap and water. That's pretty much what all of the manufacturers recommend. And what we found is now we have some long-term users. We have people using this for 9 months, 10 months, and we're finding about every quarter you have to replace that liner. In fact, we just got on the phone to the company that makes it, and we want to sew a little better edge at the top so it doesn't delaminate and can last even longer. So something like this can be sent, to third world countries or other countries. We kind of went through that. Oh, this sort of shows the differences between traditional and iFit. Much less time, much less casting, much less visits, time to getting prostheses. It is easily fit. We can do it in about an hour. I can fit them now in about an hour. This is probably the last video. This is one of our research subjects. Can you hear that? We don't have a... Why don't you plug the volume cable in for this? Because this kind of just brings it home here. And I should be done another 5 minutes, so...
There's an orange envelope on the back.
I tell you what, never mind.
Sure?
Yeah.
Okay, but it's not
is this-
that one. It's this. Where's your...
I have no idea. Right there, I think, isn't it? Turn it up a bit. Okay, so the last part of this is, so what? Does this even work? Is this sort of some flim-flam? And part of the STTR grants is you have to do research. That's where it's not just, giving money to industry to build something. You have to test it and make sure it works. So this is my son. Many of you know him. He was here at 2 years old when I was here. They won the Pennsylvania State Soccer Championship. So we did a pilot study, an efficacy study. And the goal was to determine comfort, fit, stability, and ease of use. We selected transtibial amputees who could ambulate already. We didn't want to try it being the first prosthesis. They had to be 6 months beyond amputation, and they were due to a variety of causes. And they had to have intact sensation. Where they were excluded if they had skin ulcerations or other central nervous system problems. The study was approved by the PEN-IRB, and we had 2 visits. It was a 2-week study. We brought them in, we rated their own prosthesis when they came in, and I had my research assistant rate it, so I was not present when they rated it. And then they took it home. We fit our prosthesis, the iFit device, and then they took it home. They rated their current device at the first visit. At the second visit, they rated our device, they did pressure analyses, and we did biomechanical studies on them. So we used self-reported outcome measures, biomechanics, intrasocket pressures, and monitored for problems. This is our gait biomechanics lab. We used this Fuji film to monitor the maximum pressures, and found that this is how it kind of works. It's low tech, but it's also low cost. For the comparative effectiveness study, we're going to buy a device that's about $10,000. They rated it on 7 questions. We took this from the prosthetic evaluation questionnaire, a very common instrument, but that is just huge and long, and we didn't think we really needed it. 26 participants entered the study. 4 were lost to follow-up due to challenges in transportation. No falls, no limb ischemia, and all the subjects afterwards wanted to keep the device. The mean age was 51. There were 3 females, 19 males, dysvascular and traumatic, and there were 3 persons with bilateral amputations. We did statistical analysis. We also did a worst-case scenario. So we assumed that those people lost to follow-up did worse by 1 standard deviation compared to everyone else. We assumed they're all just worse. This is the data. So with a self-reported questionnaire, assuming those people were worse off, it was still significantly better in favor of iFit device. All of the biomechanical parameters, there were no significant differences, which is kind of what we wanted. We didn't want them limping. We didn't want them having excessive stance phase instability. And so this was very reassuring here. With the peak pressures, the red is iFit, the other is conventional. It was significantly better on overall and for the tibia and the lateral leg. And it's not surprising because you have a padded liner that protects the limb. But the pressures, intrasocket pressures, were less. 2 people had minor skin breakdown, which we were addressed with changing the padding, and it readily healed up. If you look at the literature, about 40% of amputees have skin issues at some time or another. We changed the geometry of our bottom plate and did a few things that seemed to resolve that. We had 1 buckle breakage, and so that's why you're seeing a lot about the buckles. We made it from a 2-rib to a 3-rib buckle, and engineering-wise, the engineers tell me it made it much, much stronger. So in conclusion, in this very small pilot trial, it compared favorably to the other person's devices. There are no biomechanical differences. There were less pressures and slightly better self-reported fit and function. It was a small sample, though, and so it was a short term. And persons entering it, we found, may not have been fully satisfied with their conventional devices. Maybe they're more prompted to go into a study because, doc, this thing hurts. We find that a lot. There's a guy that came in, and he had been in a device, and it was the most awful thing I've ever seen. He rated it 1s. He got in ours. He rated ours 4s and 5s, and I said, boy, I like those for the study, but it doesn't tell me how well you're going to compare to a really good conventionally made prosthesis. The study strengths, however, we had objective information, not just my subjective information, pressures and biomechanics. The fact that we had significant differences with this small sample size is more compelling that maybe there's some real effects there. The biggest problem that people have complained is it appears too bulky. Can't get over their pants. They can't wear, but you know, we're addressing that, but I think the safety and reliability of the buckle over time sort of means that's kind of the way it is, and they probably have to get bigger pants at this point. We're trying a BOA system. We'll see how it works. I'm not that convinced. It does look a little bit lower profile, though. When you get the buckles out of there and you put the BOA crank on the back, it does look a little more streamlined. There's my boys. So where are we now? As I was saying, and Peggy, that's what, those are my boys. So we're at a point where we have the product, we're working on the above-knee sockets, but we need to have a comparative effectiveness study in the next 2 years, and are looking for partners, and Hopkins would be a lovely place to partner with. So there's some early users now, and what we hope is the value-cost proposition. We increase quality and decrease cost at the same time. It does work in the water. We actually got it in the water, and it floats, so it's not going to be an anchor on somebody's leg. That's what we fished for in Wisconsin. That's my son, caught a large northern pike. The above knee, we're going through that again. We have the same analyses. We're looking at an iPop, so in the hospital they can move from this socket. You can build the componentry and they can start going. I got to go, so thank you for attending. It wasn't my fault, though. We had yes.
Yeah, I was just curious, when you mentioned the cognitive dysfunction concern, judgment of patients, and patients have to have good judgment in order to do things that, is there a formal assessment process, given that we typically use assessment for other kinds of devices or procedures?
No, I think your clinical insights. In the lab, we have a pathway they go. They have to demonstrate that they can put it on and off safely. We have them go up some stairs. You'd be surprised at how many people with prosthetics aren't taught improper going up and down stairs. So we have a pathway for them to go. Any other questions? Sorry to raise there. Yeah.
How about, you talked that they said they were bulky, etc. How about appearance in general? Did they
Just bulky.
just, because again, some people wanted to kind of look a little bit closer to a leg.
Oh, the last guy, he doesn't wear our prosthesis outside. He wears his old one until I wrap foam around and he puts a black sock over it, so cosmetically it looks good. We're gonna try and get a cosmetic cover. I think that'll make a difference.
Yeah, because again, most people don't want it to be exactly like the other legs, but if it at least doesn't look like a tube, they seem to be happy with it.
I have so many patients, and again, it's a select sample. That's why we need other people working with us in that. But people say, you know, I'll trade off the bulkiness for being really comfortable. Doc, I walked all day long. I had no problems. And so there are some trade-offs there. Now,
Yeah, that has been the experience too with like high fidelity sockets, that they tend to be, in terms of shape, it looks funky, but people seem to like how it fits, and they use
I think with like the Terminator and Transformers, people are very comfortable with the machine looking. It's much different than 20 years ago. And in fact, one of our patients said, man, I really like the buckles. It looks cool. And we experimented with different colors. Initially, I thought, you know, it's going to be like a Nike line where you have all the different stuff. Finally, we just said, let's do one color, and then maybe, you know, later on. Because I think people just the technology is not scary to them anymore. Even the buckle stuff. People are used to ski boots and, you know, shoes. You know, hiking shoes have boas on them, so it's not that scary a technology.